Welcome back, class. Continuing our talks on electromagnetics, we want to continue to look at Maxwell's equations. So today we will discuss Gauss's law for the electric field in integral form. First, we're going to do a look at inspirational thought for the day. It's a verse that I really like. 1 Corinthians 1:15 through 17 states, "The Son is the image of the invisible God, the firstborn over all creation. For in him all things were created, things in heaven and on earth, visible and invisible. All things have been created through him and for him. He is before all things, and in him all things hold together." I especially like this last phrase here, because one of the still great unknowns in the world of physics is gravity, and we know how it works, but we still don't really understand why it works. We don't understand why massive bodies attract each other. And so sometimes I think maybe it's just as simple as this, that in him all things hold together. So just something to think about as we consider fields moving forward. So we're continuing in part 2 here on our outline. So there are two different equations in Maxwell's equations that are attributed to Gauss. So we want to look at the first one, Gauss's law for the electric field. In the previous equations, we've dealt with the interactions of the E and M fields around a closed path. What we want to do now is look at interactions of these fields with closed surfaces. So we do this using Gauss's equations for electric and magnetic fields. The first equation we want to look at is Gauss's law for the electric field, which is expressed as follows. It just says the sum of the displacement vector over some surface is got to equal to the total charge inside of a volume. So where this volume is contained in the closed surface S. So you have the surface S, so it has to be closed, so it forms like a sphere or a cube or whatever. So that surface and this charge rho was contained in the volume created by that surface. So in plain English, this law or equation states that the total displacement flux emanating from a closed surface S is equal to the total charge contained within the volume bounded by that surface, as I just said. So, we need to also remember, though, the total displacement flux is directly related to the electric field. So this basically says charge contained in a volume is going to create an electric field that's going to penetrate out of the surface. Now, we take into account what medium it is, and that's what turns it into a displacement flux, because that's what relates electric field to displacement flux, is the permittivity. So if we look at an image of this, we have this volume, which is, I don't know, kind of egg-shaped or whatever, and it's bounded by this surface. So we have this ds vector here. Notice the volume doesn't have a vector associated with it, but the surface does. And so these dots in here are the charges. They could be electrons or whatever you want them to be, but they are creating this total charge inside this volume, and so they're causing this displacement field to emanate from that charge. So this law can be derived from Ampere's law as follows. If we consider the surfaces S1 and S2 that are both bounded by the same closed path C. So if we look at this image, if we took this closed path and just the S1, remember that's the original scenario that we had when we were dealing with Ampere's law. But now we're going to create another surface on the other side of this to create a volume. So it's like you're blowing bubbles through both sides of this at the same time. So you'll have S1, S2, they're kind of sliced in half or in two pieces along this circle C. And so they will have surface vectors, of course, associated with them as well that are normal to the surface at all points. So in doing this, we'll realize that in applying the law of conservation of charge, that we can relate the volume current density vector J to the total moving charge as follows. So we can say that the current is just the flow of electrons, right, or the flow of charge. So over here, if we have a volume and we have a charge that's changing over time, it's got to be flowing. So in that sense, it is a current. Same thing here, if we have a current density traveling over a surface area, then by definition, we've talked about that before, that this is also a current. So we're just saying here, these are, for more or less, two ways to define or to characterize current flow. So we can rearrange this equation then to say that the total current flow plus the change in the charge inside of a volume has got to equal to 0. So one way that you could think about this then is to say that the total current due to flow emanating from a surface is equal to the time rate decrease of the charge within the volume. So in other words, we have charge in this volume. As it starts to flow out of the volume, of course that creates a current, but it's also reducing the charge, total charge inside the volume. So now, if we can examine our original surfaces and apply Ampere's law to both surfaces, so we can say that the magnetic field intensity around this circle has got to equal to the current flow and the displacement current on surface 1. But we could also say that this magnetic field intensity around this same closed surface path has got to equal to the total current flow and the displacement current on S2. Well, we notice that so you have the same thing on the left side of this equation. So that would allow us to combine these to say that the total current flow through S1 and S2 plus the total current displaced with S1 and S2 has got to equal to 0. If we now apply the results from this conservation of charge relationship earlier, then we will have that the time change of the charge inside the volume plus the time change of the displacement current on the surface has got to equal to 0. Well, we can now relocate the differential operator because they're both taking the derivative with respect to time all the way outside of this equation, which gives us this new equation. So as we look at this equation, the derivative with respect to time of whatever's inside of here has to equal to 0. Well, we see there is no dependence on time in here that we're aware of. So the only way that this could be true is for the expression inside the brackets to be a constant in relation to time. So we could rewrite this then to say that the sum of the displacement current or displacement field vector over the surface minus the total charge inside the volume has got to be constant with time. So here we take kind of an experimental liberty to say that since there's no experimental evidence that suggests that the right side of this equation is non-zero, we can set the equation equal to 0. So this yields that the total sum of the displacement vector over the surface area has got to equal to the total charge inside the volume created by that surface area. This is Gauss's law for electric field. So let's look at a quick example then. We're going to have this point charge Q, and it's going to be situated at the origin of a sphere defined by some surface, and we want to evaluate or find the D field, or the electric field displacement field vector as a result of this over the surface. So according to Gauss's law for E fields, we have that the sum of this displacement vector over the surface has got to equal to Q. Remember before it was the total charge inside a volume, and so we already know the total charge in there is just this test charge Q, or point charge Q. So considering the symmetry constraints and realizing that this displacement vector is normal to the surface everywhere, we can see here it should be normal everywhere. This would suggest then that we can bring the d out of the integral, and the dot product will just yield 1. And so now we're just integrating the surface, find out the total surface of the sphere. So it's supposed to be d times the surface area of the sphere. Well, we know from earlier math that we can calculate that as just saying 4 pi a squared to get the surface area. And so the result then is that 4 pi a squared d has got to equal to q. So now we do just a little bit of rearranging, and we find that our displacement vector is just equal to the total charge inside of this divided by the surface area at any distance a. Actually, we could let a vary or be anything we want. And so what this is kind of saying then is that the charge is being equally distributed across the sphere surface. So, you know, the bigger you make the sphere, the more the charge is spread out. So, consequently, the d vector will decrease in intensity at each point on the sphere.